Microsoft has announced the creation of a new quantum chip called Majorana-1, and my dear viewers have repeatedly asked me to explain the essence of the discovery. To answer briefly, it's about a fundamentally new technology for creating qubits, the key building blocks of quantum computers. In this case, it's about qubits that will have an unprecedented level of protection against external influences compared to other technologies. This, in turn, will enable the creation of truly powerful quantum computers with hundreds of thousands and millions of qubits on a single chip, as opposed to the dozens, or at best hundreds of qubits used by quantum computers today. If we get more specific, the Majorana-1 chips are expected to use so-called topological superconductors to create qubits, in which under certain conditions, special states known as Majorana-0 modes can be created. These modes are spatially separated within the superconductor, thus implementing the very topological protection of qubits. If the previous sentence sounded like complete nonsense, that's perfectly normal. Topological qubits are a rather non-trivial technology, understanding which requires deep and specialized knowledge of quantum mechanics and condensed matter physics. In today's video, I will try to explain as briefly and generally as possible what this is all about. And it's worth starting with the question, what exactly is a qubit? In ordinary classical computers, data represented as zeros and ones is stored in elementary cells known as bits. Bits are special material objects capable of existing in two states like on and off, allowing them to be used for encoding binary information. A bit in the off state corresponds to 0, and a bit in the on state corresponds to 1. The general operation of a computer consists of taking incoming data as sets of bits and, according to certain algorithms we have established, transforming them to produce another set of bits. For example, the result of a mathematical operation or something else. In quantum computers, essentially the same thing happens, but instead of bits, quantum bits or qubits are used. These are also physical objects, but they obey the laws of quantum mechanics. They can also be in state 0 or 1, but unlike classical bits, their state is not determined with certainty. Instead, a qubit takes the values 0 or 1 with a certain probability, and the characteristic of a qubit is precisely the ratio of probabilities of obtaining 0 or 1 upon measurement. It is said that the qubit is in a mixed superposition of states 0 and 1. It is precisely due to the ability of a qubit to be in a superposition of states, along with some other of its quantum mechanical properties, that quantum computers have additional capabilities unavailable to classical computers. For example, the ability to very quickly solve certain classes of mathematical problems that would take even the most powerful classical supercomputers years or more to solve. We discussed how and why this happens in a separate video dedicated to the principles of quantum computing and the discipline known as quantum computation theory. We will not delve into these issues now. Suffice it to say that to solve real, practically meaningful problems, quantum computers must operate with thousands, tens of thousands, or preferably millions of qubits. And this is where certain problems arise. Quantum mechanical effects on which qubits operate are rather subtle, and the qubits themselves turn out to be extremely sensitive to various types of interference and noise. Such noise can cause the information stored in qubits to spontaneously distort, meaning the states of qubits can change under disturbances at the most unpredictable moment and in the most unpredictable way. That's precisely why quantum computers require specially prepared environments protected from external influences, and the quantum chips themselves are placed inside huge tanks, where the necessary vacuum and ultra-low temperatures are created for their operation. Unfortunately, even these measures do not solve the problem. Even if we completely shield the quantum chip from external noise, there will remain the noise generated by the qubits themselves during their operation and state transitions. And the more qubits there are in a quantum chip, the stronger the noise and the higher the likelihood of errors. This is exactly why today we cannot create functional quantum chips with a large number and density of qubits. Technically, it is possible to physically cram many qubits onto a chip. For example, the Condor quantum chip contains 121 qubits, but due to high noise and a large number of errors, making it do something useful turns out to be problematic. And yet, to solve real-world problems, we need tens, hundreds, or even thousands of times more qubits. And all this looks very much like a fundamental dead end. And this is precisely where Microsoft offers a way out of this dead end by creating so-called topologically protected qubits, which will be less susceptible to external noise and therefore will be able to more easily coexist with a large number of other such qubits while maintaining functionality. The core of a Majorana qubit is a very thin superconducting wire, a so-called nanowire, with a thickness of just a few tens of nanometers. This is important so that electrons inside such a conductor can only move along it, making the system one-dimensional. To be more precise, we are not just talking about a superconducting nanowire, but a nanowire made of a topological superconductor. Most often, we are talking about a semiconductor made of a material with strong spin-orbit interaction, like indium arsenide, where superconductivity, or more precisely, p-type superconductivity, is induced by contact with a real metallic superconductor, like aluminum, at very low temperatures. Why such a construction is needed, what p-type superconductivity is, and how it differs from classical s-type superconductivity and other very important things, we will not discuss now so as not to dive into the depths of superconductivity theories and topological states. By the way, the latter represents a rather interesting concept with great potential for practical application. For now, we will not go deeper into this, and will just state that the core of a topological qubit is a superconducting topological nanowire. Whether a qubit is in state 0 or 1 is determined by the number, or more precisely, the parity of the electrons present in it. An even number of electrons corresponds to 0. An odd number corresponds to 1. It should be understood that in a nanowire, as in any superconductor, electrons are paired in special states known as Cooper pairs. The number of such pairs in the conductor doesn't really matter. However many there are, the total number of electrons in such pairs remains even. However, the number of electrons in such a system will not be constant. Some electrons can enter the superconductor by tunneling from outside, others can leave the superconductor in the same way, or they can be knocked out of the superconductor by incoming photons. This is a random, poorly predictable, and weakly controlled process. But we can make life easier if we imagine the ensemble of electrons inside the superconductor like this. Actually, it doesn't matter much how many, number of electrons in Cooper pairs, which may even be non-constant, plus one unpaired electron, which may or may not be present in the conductor. The presence of an unpaired electron affects the physical properties of the nanowire, for example, its superconductivity, and by performing the appropriate measurement, we can determine whether this electron is present or not. If it turns out that it is present, then the total number of electrons is odd, and we will say that we have detected the qubit in state 1. If it turns out that it is not there, then all the electrons are paired, their total number is even, and we will say that the qubit is in state 0. However, between measurements, we cannot say whether it is there or not. According to the standard approach of quantum mechanics, we can only talk about the probability of finding or not finding the unpaired electron during measurement. In other words, before measurement, our qubit will be in that very mixed state, a superposition of the states unpaired electron present and unpaired electron absent. And the ability of a qubit to be in a mixed state is precisely what we need from it. However, as we mentioned above, the number of electrons in a superconducting nanowire can change under the influence of external, random, unpredictable factors. The probability of finding or not finding it can also change, i.e., the state of the qubit can change. But taking into account the very features of the topological superconducting system, which we have not delved into in detail, it turns out to be possible to protect the state from the effects of small, weak perturbations and make it more resilient to them. A proper explanation of the protection mechanism, the so-called topological protection, would once again require us to dive deeply into the physics of condensed matter. So I will explain it as simply as possible and hope that I have not oversimplified it too much and made the explanation incorrect in the process. Let's imagine that each electron in our superconductor can be at some particular place. Depending on the number of these places and the number of electrons, some of these places will be occupied, others unoccupied, and one of them will be partially occupied and partially not, in the sense that, upon measurement, we may find it either occupied by that very odd electron or empty with some probability. In a completely standard way for semiconductors, we can now say that electrons are located in the occupied places, or, as physicists say, in occupied states, while quasi-particles called holes are in the unoccupied ones. The term quasi-particle means that we understand there are no actual particles there, but it's convenient to think as if they are present. As for the partially occupied state, we can say that it contains a certain quasi-particle, which is a superposition of an electron and a hole, meaning that when we look at our conductor and ask it how many electrons it has inside, this quasi-particle will become either an electron, i.e. a real particle, or a hole, and what it turns into will determine the state in which we find our superconductor. So here's the thing. The trick of one-dimensional topological superconductors with strong internal spin-orbit interaction is that if you place such a conductor in an external magnetic field, you can sort of split our electron-hole superposition into two quasi-particle halves, and these halves will tend to be at opposite ends of the conductor. You could say that each of them will be a superposition of half an electron and half a hole. If all this seems completely insane and some sort of casuistry to you, that's perfectly normal. When I first heard about this concept, my brain practically exploded. When I tried to figure out what was meant here, my brain exploded repeatedly and each time more and more intensely. I will try to spare my dear viewers from such an experience and suggest a relatively simple, though not entirely correct analogy of what we are talking about. Imagine that our snake of electrons sort of oscillates from side to side. Because of this, the extreme holes of our wire end up either being occupied by an electron or not. That is, observing our conductor at any given moment, we can find, for example, an electron on the right and a hole on the left, or vice versa, an electron on the left and a hole on the right. In other words, our additional unpaired electron is sort of evenly split between two places in the conductor. We cannot say in advance exactly where it is, but we only know that it is somewhere at the edges of the nanowire with a certain probability. Again, the analogy is not entirely correct. In it, our electron is always actually either on the right or the left, and the only question is that we don't know where it is until we look. But here we have a quantum mechanical situation. Until we look at the conductor, the superposition of the electron and the hole will indeed be smeared between the two locations, or, as physicists say, localized at the edges of our nanowire. And these localized states of our quasi-particle, representing a superposition of an electron and a hole, are called Majorana-1 modes. Why are they called that? The reason is that separately, these modes have no physical meaning. If the original quasi-particle we split into modes is a superposition of an electron and a hole, then a Majorana mode is a superposition of half an electron and half a hole, but neither half an electron nor half a hole can exist. Physical meaning will only emerge when considering both Majorana modes together. We can return to our analogy of the oscillating electron snake. By looking only at one end of it, we cannot say how many electrons it contains, or even whether their number is even or not. We can only state whether we have detected an electron at this particular position. To count the total number of electrons, we need to look at the entire snake, including both of its ends. And since we cannot determine what exactly a single Majorana mode is, we also cannot detect any difference between them. That is, the Majorana modes turn out to be fundamentally indistinguishable from each other. But at the same time, we know that if we combine both Majorana modes, they will disappear, generating the original superposition of the electron and the hole. This is very much like the annihilation of a particle and its antiparticle. And here physicists recalled the existence of objects whose existence was theoretically predicted by Italian physicist Ettore Majorana back in the first half of the 20th century, the so-called Majorana fermions, which are their own antiparticles. In physics, such particles are also called truly neutral particles. Examples of truly neutral particles include photons. Two photons, in general any photons, can annihilate, forming other particles. More precisely, particle-antiparticle pairs, such as an electron and a positron if they have sufficient energy. However, photons are gauge bosons, or drops of energy. We have a separate video detailing the types of elementary particles. With matter particles, i.e. fermions, it's different. There are no truly neutral particles among them, and we can always distinguish a particle from an antiparticle. For example, positrons and electrons have opposite electric charges. Such fermions are also called Dirac fermions, named after the Frenchman Paul Dirac, from whose equations the prediction of the existence of antiparticles was first made. And just as Dirac discovered on paper that particles and antiparticles must exist in the universe, Majorana showed that there should also be truly neutral fermions, whose antiparticles would be indistinguishable from themselves. We have not yet observed Majorana fermions in practice. More precisely, some scientists believe that neutrinos may be Majorana fermions, although others strongly disagree, pointing to experiments that supposedly prove that the nature of neutrinos and antineutrinos differs. We discuss this and much more in a separate video dedicated to the mysteries of neutrinos. It's possible that other Majorana fermions exist in nature. We just haven't encountered them yet. However, our quasi-particles of half-electrons behave exactly as those Majorana fermions should behave, in the sense that they are fermions, indistinguishable, but at the same time capable of annihilating to form other particles. It is precisely because of this analogy that these quasi-particles are sometimes called Majorana fermions. However, to remember that these are not real particles, but merely special states of an electron ensemble, they are more often called Majorana modes, or more precisely zero modes, because their energy exactly corresponds to the Fermi level, which in solid-state physics is usually taken as the zero level. This is actually important, but to explain why, I would have to explain the Fermi level, other energy levels, and their positions relative to the Fermi level, which would take me another 20 minutes of your precious time. So we'll leave that aside as well. If anyone is very interested in what the Fermi level is and how it fundamentally distinguishes conductors, semiconductors, insulators, and superconductors, write in the comments, and I'll make a separate video about it, where we'll also mention Majorana zero modes. For now, let's focus on the main point. In a superconducting topological qubit, its quantum state, that is, the probability of finding an even or odd number of qubits, can be reduced to the state of a quasi-particle, which, upon measurement, with a certain probability, will turn out to be either an electron or a hole. We can change the qubit state by altering the probability of obtaining an electron or a hole upon measurement. This state can change due to our intentional actions during quantum computations, which is good and proper, but it can also change under the influence of random factors without our knowledge or intention, which will spoil the computation results. And that, on the contrary, is bad. So it turns out that splitting this state into Majorana modes, located at different ends of the qubit, makes changing this state significantly more difficult. Both of our Majorana modes are inseparably connected to each other, since they are like halves of the same quasi-particle. If this quasi-particle was in the state of the electron is definitely present, then upon measurement, we must find this electron at one end of the conductor or the other. And if we detect it, for example, on the right, then we will not be able to detect it on the left. And if we do not find it on the left, we definitely know it is on the right. In other words, the states of Majorana modes turn out to be interdependent. This is somewhat similar to quantum entanglement. But while quantum entanglement can be easily destroyed if you try to change the state of one of the particles in the pair, the situation here is more complicated. It turns out that changing the state of one of the Majorana modes without changing the state of the other is impossible. To change their state, You need to act on both modes at the same time and in a very specific way. It's not that this is impossible. If it were, we wouldn't be able to change the states of the qubit, and all our efforts to create a topological qubit would be practically useless. But to do this, you need to make a known effort. And more importantly, you need to apply this effort simultaneously and synchronously to different ends of our nanowire. This is precisely why topological qubits are capable of ignoring many types of noise that would otherwise disrupt their operation, making them more resistant to disturbances, or, as it's also called, topologically protected. But the main point here is that thanks to topological protection, we can build a functional quantum chip containing thousands, hundreds of thousands, and millions of topological qubits, which is what makes this technology so groundbreaking. Or rather, it will be when it's realized in practice, because there are serious doubts about whether Microsoft has actually managed to implement it. And here we move from theory to practice, from how the Majorana-1 chip is supposed to work to how it actually works. Let's start with the main point. There are no millions of qubits in the Majorana-1 chip at all. So far, it only contains 8 qubits. So by quantum chip standards, Majorana-1 is nothing extraordinary yet. Moreover, so far, no one is even saying that Majorana-1 with these 8 qubits can actually compute anything. As far as we can tell, this hasn't been tested at all. On the other hand, this is not even required. Majorana-1 is an experimental prototype whose task is to demonstrate the very possibility of implementing this technology in practice. But even with this, there are problems. If you carefully read Microsoft's press release, you won't find any clear statement that they created topological qubits. Instead, much more vague phrases like new topological architecture and similar expressions are used. Microsoft only confidently claims to have created a material in which Majorana particles can be observed and controlled. That is, a material where the very spatial separation of electron and hole halves can be achieved, a key requirement for creating topologically protected qubits. And if you read not the press release, but the scientific paper published in the Physical Review journal, it turns out that even the developers themselves are not entirely sure about this. They did indeed register some quasi-particles at the ends of the nanowire, which generally resemble Majorana zero modes. But even they are not sure that it was really them, and not, for example, so-called Andreev states, very roughly speaking, oscillations of electrons that strike and reflect from the superconductor's boundary. Moreover, many scientists doubt the reliability of the evidence obtained. For example, Dr. Henry Legg, an expert in condensed matter theory and quantum computers, criticized the experimental data analysis protocols and stated that the main claims are primarily based on unexplained variations in measurements and inconsistent definitions, rather than on the intrinsic properties of the devices under study. Finally, even if all doubts are dispelled, if Microsoft has indeed managed to create a topological conductor with Majorana zero modes, and even if we are shown truly working qubits and a chip based on them, this still does not guarantee the imminent arrival of a bright quantum computing future. The researchers themselves emphasize that creating topological superconducting nanowires is an extremely delicate and complex process that requires literally atomic-level assembly of key devices. And if that's the case, then creating even dozens or hundreds of qubits with this technology could be so complicated and expensive that it would render the entire endeavor pointless. In general, I would personally hold off on celebrations and fireworks about the dawn of a new era in quantum computer development, although, of course, I would love to hope for the best. And if you enjoyed this video, I kindly ask you to support the project by becoming its sponsor, here on YouTube or on Patreon and Boosty. All the necessary links will be in the video description. Once again, thanks to all our sponsors, those who are already supporting the project, and those who decide to start helping the channel now. And that's all from me, dear friends. Take care, and see you next time.